Not a lot.
Okay.
Cool.
In 3.
Cool. Alright. Today, we're going over our design review for the solar T.R.E.E. Bluetooth car. We are T.R.E.E., the real electrical engineers.
I'm Chris Padilla, analyst, digital hardware design.
I'm Ashley Patillo. I'm the recorder, the spokesperson, and the systems engineer.
I'm Tristian Seegars, the leader, pessimist, and I'm also dealing with analog design.
I'm Ronnie Stevenson, the optimist and the software developer.
And our advisor and slash customer is you, Dr. Lee. Our motivation for this project was given to us from our customer slash advisor, and we're trying to contribute to the use of renewable energy and also help decrease air pollution. This right here is a chart, again, showing you the different types of energy that we use. The big chunks of it are the non-renewable sources, and we're trying to get the renewable sources used. So we're going off the solar.
This will be our overview for our presentation today. We will go through our requirement specifications, the proposed design, the design test that we did, and also our project plan. So basically, the overview for our project will be a Bluetooth controlled and solar powered car, charged car. And the system will allow the solar charged power to supply power to the microcontroller. So once it's powered, then the user will be able to control this RC car using a modern Bluetooth device. For the engineering specifications, the first one will be a smart device will operate the car. As I stated, modern Bluetooth technology. The car will utilize Arduino technology. The car will connect to Class 2 Bluetooth radio receivers. The car will be connected to one controller at a time with no interference from any other controllers. The charging system of the car will shut off once the battery has reached its max charge. The solar panels will charge the car's battery. The battery's charge time will be less than 6 hours. The solar panels will be waterproof. The car will remain stable in winds up to 40 miles per hour. And at the car's top speed, the solar panels will remain operable even after impact with other objects.
This right here is breaking our project down. This is the first level of our project, which is level 0. And this is the block diagram we have. We have 4 different, 2 inputs, 2 outputs. We have the solar energy and user control as the input to our whole system. And then we have DC power coming out and the user operation of the car. This right here is our level 1 block diagram. It shows you the inside modules of the level 0 diagram. The same main inputs and outputs, but inside we have the controller module, communication module, power supply module, and the processor module. These right here are the functionalities of each one of our modules: the power supply, processor, communication, and also our controller. For the power supply, we have the solar energy going in, DC power coming out. The processor, we have data transmission going into it. We have DC power coming out, and we also have user operation of the car from the processor. The communication system, we have data receiving, leaving, and we're coming in, and then we have data transmission coming out of the communication system. The controller, the inputs are user control, data transmission, and the outputs would be data receiving.
Okay, so this is our level 2 block diagram. We broke down the power supply. Our main input is solar energy that goes into the solar panel. From there, it splits. Parts of it goes to a dual battery pack, parts of it goes to a switching processor. From a switching processor, it goes back and forth between the dual battery pack. And our main output for the level 2 is DC power to whatever processors need power. And this is the functionalities. Switching power, this is where the processor will communicate with the dual battery pack to decide which battery needs to be used and which battery needs to be charged. Solar panel is just how the whole system gets its energy. In a dual battery pack, like I said, you have two different batteries. One's charging and one's being used at the time. This is the UML diagram. The flow of the diagram starts with the open circle. From there, it checks if the switch is on and off. If it is in the on position, then it proceeds to the fork. You have three different processes going on during the fork. You have the charging system, which is on the right over here. You have it checks the power of battery 1, compares the power to battery 2. If battery 1 is greater than battery 2, then battery 1 is switched to power mode, battery 2 is switched to charge mode. If battery 2 is greater than battery 1 is switched to charge mode, and battery 2 is switched to power mode. After that, it charges for about an hour. If the off switch is turned off, then it breaks out and it turns off. If not, then it cycles through and continuously checks. The data, the RX data and the TX data is basically transmission and receiving data from the controllers. The RX data checks the controller for incoming data. So if the controller's sending a signal, then it stores the signal in the memory, then it goes to transmit data. If it's not, then it continuously loops and continuously checks to see if the controller's transmitting data. And then the transmit data process, it sends the signal from the memory to the processor, clears the memory, checks the memory, then checks to see if the memory is empty. If it is, then it goes back to the receiving data sub-process. If not, then it cycles through the process. And that's really, the transmitting data and receiving data is a continuous loop of transmitting and receiving data from the controller.
This right here is our test document that we came up with to meet our engineering requirements for the solar panel.
So description, solar panel unit test will verify whether the solar panel unit will provide a sufficient voltage to charge the battery under different levels of light. And the engineering requirement that it uses is solar panels will charge the RC car battery. And this is the test the full test after we tested it. This is the 6-volt solar panel that we used in testing. The process of testing it, we isolated the solar panel, completely uncovered and under a lamp. Then we read the voltage. Next, we covered up 25% of the solar panel and read that voltage. After that, we covered up half the solar panel, read that voltage. Covered up 75% of the solar panel, read that voltage. Then covered up 100% of the solar panel and read that voltage. After all of that was complete, then we did the whole process itself of being under a lamp, which is there under normal lighting, so just under a normal room light. So after that, I just explained all the actions, expect the results. When the solar panel is uncovered and under a lamp, we should get 6 volts. When it's 25% covered, we should get 4.5 volts. When 50% is covered, we should get 3 volts. When 75% is covered, we should get 1.5 volts. When it's completely covered, we should get less than 1 volt. Likewise, when it's just under normal light and it's uncovered, we should get 4 volts. When it's 25% covered, we should get 3 volts. When it's halfway covered, we should get 2 volts. When it's 75% covered, we should get 1 volt. And then when it's completely covered, we should get less than half a volt. And that explains the whole test. That's the whole test.
These are the circuits that we use to model the solar panels.
So, Dr. Lee, what we use as a CAE tool, we use P-Spice to kind of model the solar panels. So we use like a RC circuit kind of to model it. So what we did is we took the voltages that the solar panel was giving out, and we used that as a power source. And what we did is we used the capacitor to kind of act like a battery, because it's going to kind of charge up our battery. And from that, you know, we got our several different voltages. So in this case, this is our test when we were doing under regular room light. So our test results are actually up there in the voltages. So we have one of them, I see right here that in the second circuit right here, it was at max, so at our max voltage when it was like, it wasn't covered at all, we got 4.37, so on and so forth. So this was actually the best way to model it because we didn't have exactly a CAE to model it in the actual component itself, because as you know, a solar panel, it's affected by the elements and everything. So this was like the closest thing that we got to it.
Just to simulate the behavior.
Yeah, simulate the behavior almost of the solar panel. So right now, and I have some pretty looking graphs for you as well, if you can't see it, kind of right there. Right now what you're looking at is our testing when we did the solar panels in room light temperature. So we did a voltage versus time graph. So it charged up really fast, and if we actually had the tools here to show you, so we would need a voltmeter, all that stuff, and something just like a piece of paper to cover it. But it charged, the solar panel would charge actually relatively fast. So the graph kind of shows that. And right now, as you can see, the top voltage, the red line, is when it was not covered at all. Blue line right here, 25%, 50, 75%, none. Like it was just completely covered totally. So going off our testing document, it looked all right. It looked pretty good, I would say, from the results. And then we did the test again, because in our testing document, we did room light and then we did direct light. In direct light, and direct light gave us a lot better voltage, because the solar panel was capable up to 6 volts, right?
Yes.
So 6 volts, and we got basically that. So it was really good. It basically tested out right. So under just direct lamp light with nothing covering it, we got 6 volts. So that's actually perfect for, you know, if we just wanted to charge it like that. And then again, so the red line is 100, or it's not covered at all. Blue line was covered 25%. Yellow line was covered 50, purple down here, it was covered 75, and then the blue line down here is when it was just fully covered, period. So all in all, the testing went kind of all right, if I do say so myself.
Yeah, the testing went good. The only inaccuracy that we found was the yellow line at 50%. That line was a lot closer to the 25% line than expected, and the reason we explained for that is maybe inaccuracies. Maybe with solar panel, the lower voltage you get, the more inaccurate it puts out. But that was the only problem. Except for that, we considered the testing to be successful.
Yeah, I just say solar panels, they're dependent on, you know, everything that's going on, and I feel like this was actually the best way to model it. So it went pretty well.
This right here is our work breakdown chart for splitting the work between the whole project. Right here with the major bullets are software, software activity, power activity, car development, and system integration test for the whole thing. Under the software, we have to actually purchase software. We have to develop the code for the software, download and test the programming. Under power, we have to design our power circuit, purchase our power components, and also construct and test. And then as far as car development go, we have to purchase parts, construct car, and then we have to integrate everything after these right here, the predecessors, show you what has to be done first in order to actually finish that project. So as you see right here, to construct the car, we have to actually have our software design finished and our power design finished before we actually construct the car. And then we have to have all of those done before we can integrate the tests, have them integrated together. Oh, and also, it shows deliverables, the checkpoints that we days it should take, and the people involved in each activity with the number beside them, meaning the level of responsibility. So one is primary responsibility, and two is secondary responsibility for that action. This right here is just our Gantt chart. It shows the same thing as our work breakdown, but it shows it as a time over the course of our project time we have. Actually gives you a visual of when things should start and when it finish. Right here it shows us finish on our project sometime in April. And Yes, these times are basically based off of, again, what it should take, and like, I guess, as far as purchasing parts, you gotta wait for them to get here, things like that. And code development and power, they're big time blocks, because there's gonna be a lot of work involved in getting those activities done.
So right here is our nice little cost analysis sheet. So over there in part name, we have all the parts that we actually need for the project, kind of when we brainstormed it out. So for the whole project, we're going to need an Arduino board. That's the actual microprocessor that's going to, host the Bluetooth functionality. We're going to use a PlayStation 3 controller to move the car, so that's going to be our user input. We're going to need 2 USB dongles, Bluetooth dongles, because we're going to use that as a wireless transmitter and receiver, so we don't have to actually hook it up USB, because you don't want to follow it around and everything, and the whole point is to make the Bluetooth receive the car. We're going to use the host shield. Now, the host shield, I actually did a little research myself. The host shield is actually a hookup to the Arduino board to help make Bluetooth functionality a lot easier than actually going through setting up jumpers, setting up the UART from board to board. So it's basically a nice little booster pack, if you will, to the Arduino board. So it would help make our project a lot easier. And then we have the solar panel, of course. Solar panel is going to be the power of the car and everything. So as you can see, those are all the parts we needed. The providers, I did a little research, on Black Friday, but I'm pretty sure that's actually the best cost, because we got in our part sheet on time. So all these parts should be actually coming in. So we're getting our Arduino board from the actual manufacturer. We're getting the PlayStation 3 controller and the dongles off of Amazon.com, because it was pretty cheap on there at the time. The host shield was offered through multiple people. I'm actually getting it from the actual website from there, or you could have used we could have used SparkFun. A lot of people I see use SparkFun. And then solar panel, Tristian actually went to Radio Shack, and he said they have a nice little selection of solar panels of what we need.
We already have one purchase right there.
Yep, and we already have one purchase right here. So current state, everything's pending right now. I did just put in an order form for the all of the wireless and Bluetooth stuff. Unit cost, pretty self-explanatory. That's how much everything's going to cost. Right now, it's looking like it's going to cost around close to $100 right now just for these parts alone. We only need one of everything. And as I said, went through the Arduino board, justification, Arduino board, Bluetooth setup, controller, PS3 controller is going to be actual control it. The dongles will be receiving and transmitting data. The host shield makes Bluetooth functionality a lot easier on the programmers. And then solar panel is powering the car.
Just a quick question on that 2X mini USB number 3 there.
Mm-hmm.
So it comes in one unit, it has 2?
Yes.
Okay, alright.
So in conclusion, for this presentation, the design for the project will meet the indicated critical requirements that we explained earlier. It will also implement the proposed design process. It will implement various tests to monitor the efficiency of the solar panels and will stay within the proposed cost chart that Chris just explained.
Thank you for your time, Dr. Lee. We really appreciate you coming out, sitting down and listening to us.
Okay.
Any last minute questions you have?
Oh yeah, I got a couple questions. Well, first off, I am sorry I was late today.